Hello, and welcome to today's Electronic Design and Microwaves and RF webcast. Our topic today, technology advancements in data storage and system interfaces for high-speed data recording, is sponsored by Mercury. I'm David Moliniak with Endeavor's Design and Engineering Group. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply type your issue into the Ask a Question box and a member of our team will assist you. You can also click on the question mark help button in the upper right corner of the screen. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the Ask a Question box and click on the Send button. If you would like a copy of the presentation, please click on Event Resources on the side of your screen to download the presentation. Also, please be aware that today's session is being recorded and will be available on the Electronic Design and Microwaves and RF websites within the next week. You'll be notified by email when the archive is available. Now let's meet today's speaker. Chris Tojira is the Senior Principal Product Manager for the Recording Systems product line of Mercury. Chris has over 26 years experience in the electronics industry and has held positions as a senior software engineer, strategic account engineer, and applications engineering manager for Pentec, now part of Mercury. Now let me turn things over to our presenter. Chris, the floor is yours.
Hello everyone, this is Chris Tojera. I am the product manager for Mercury's line of Talon recording systems. And today's webinar will be on technology advancements in data storage and system interfaces for high-speed data recording. Let's get started. So to give you an idea of where we're at with our current technology, our Talon data recorders are currently capable of sustaining recording rates up to 12.5 gigabytes per second. These are real-time recording systems that include hundreds of terabytes of data storage, which results in hours of real-time signal recording. How we get there, that's the nature of this presentation. What we're going to talk about is how we leverage COTS, commercial off-the-shelf hardware, and how the advancements in the technology that's driven by the data center and gaming markets allows us to move faster and faster with our record speeds. We're going to talk about PCIe and how its continual updates generation to generation has doubled speeds and has opened up bottlenecks, allowing us to move data faster and faster to disk. We'll also talk about disk technology and the advancements that have been made over time, all the way back from the days of serial ATA interfaces to the current NVMe drives. And finally, we'll discuss a little bit about RAID technology and how RAID allows us to stripe data over multiple drives in a system to provide higher aggregate storage rates and higher capacities in our recorders. So a little bit of history on our recorders, where they've been and where we're going. In 2010, we announced the Model 2706, which was a 4-channel recorder, had 4 200 megasample per second A to D converters, and it had a maximum record to disk rate of 2 gigabytes per second. I have some figures here that correspond to the amount of IBW that could be captured on both a single channel and 8 channels that would correspond to a 2 gigabyte per second rate. So it gives you a feel for the bandwidth of the signals that could be captured. Again, this is 2010, 2 gigabytes per second. 3 years later, in 2013, we introduced a 4 gigabyte per second recorder. In this particular recorder, the Model 2749, we included a single channel 3.6 gigahertz A to D. But again, we doubled those record speeds to disk in a matter of 3 years. 3 years later, another doubling, up to 8 gigabytes per second. This was an excellent number for us, as we had at the time a 16-channel 250 megasample per second recording system that produced 8 gigabytes per second of data. So again, doubling speeds every few years here, leveraging commercial off-the-shelf PC technology and disk storage technology to get there. In 2020, we announced a 12.5 gigabyte per second recorder. This was an important number for us, 12.5 gigabytes per second, because what we found was we were capping out what we can do with serial ATA drives. We had to move to a different drive storage technology to get there, but more importantly, this number corresponds to the full line rate of a 100 gigabit Ethernet interface. That's critical because our newer products, including the RFSoC, uses 100 gigabit Ethernet for offloading data. So building a recorder that was able to ingest the full amount of data that could be produced by an RFSoC was critical, and we reached that milestone in 2020. Moving forward, we have a roadmap to get to 25 gigabytes per second, and that's happening this year. We're able to, again, leverage commercial off-the-shelf technology, new generations of PCIe, as well as new storage technologies. But most importantly, this will give us the ability to handle 2 channels of 100 gigabit Ethernet, and that number is a big important number because of the architecture, again, that we'll talk about with the RFSoC and some future products. To give you an idea of some of the form factors that we have and what data rates they're able to hit, we'll start with our rack mount recorders because these are our fastest recording systems. They come in a 19-inch chassis. They have all front panel removable solid-state drives. This is an important feature that we'll talk about as we evolve storage technologies. A ton of capacity can be added here, up to 244 terabytes, which results in hours of real-time recordings. The highest streaming record rates are in this chassis. This is the chassis that's currently hitting 12.5 gigabytes per second, with the next generation targeting 25 gigabytes per second. And we've done this, we've hit that 12.5 gigabyte per second mark, leveraging PCIe Gen 3 motherboards. But the migration to Gen 4 is what's going to allow us to move to double that rate to 25 gigabytes per second. Traditionally, we've included SATA drives, up to 32 of them, front panel removable, and that got us to the 8 gigabyte per second record rates that we had in the past. But now moving to Gen 3 NVMe drives, we're able to, with far fewer drives, sustain rates that are far higher and that are more in line with the interfaces that are piping data off of our data acquisition cards. The portable recorders, again, a very nice package because of its ability to move in a laboratory environment from site to site or in a deployable environment from site to site. Has removable drives, can handle a large capacity up to 122 terabytes. In the past, it has had a maximum streaming recording rate of 4.8 gigabytes per second, and that was limited by the number of drives that could be included in the system. Again, this is older drive technology, serial ATA, but the next generation here, we're targeting 12.5 gigabytes per second, and that will be using both newer motherboard technology, the Gen 4 from a Gen 3, and the newer drive technology, moving from the 16 serial ATA RAIDs to, serial ATA drives to U.2 NVMe drives. And we'll get into those drives and those PCI motherboards shortly in this presentation. One of the more impressive packaging recorders that we have is our small form factor recorder. It comes in a very small footprint, with a low power consumption and low weight, so it's optimized for size, weight, and power. Achieving very high data rates in a package like this is challenging because there's only so many drives you can fit. So traditionally, we have built this with a removable quick pack that can hold up to 61 terabytes. Again, a limited number of serial ATA drives are included in that quick pack, so both the speed and the storage capacity were limited. 4 gigabytes per second has been the max rate we could hit. This next generation, we're targeting, again, 12.5 gigabytes per second, which is unprecedented in a form factor like this. For that matter, 4 gigabytes per second was unprecedented. Moving to 12.5 is really impressive. Targeting more storage as well at 122 terabytes. Moving from a Gen 3 motherboard, we will actually be we will need to move to a PCIe Gen 5 motherboard to hit these higher speeds due to the number of physical PCIe slots available in a package this small, as well as the amount of drives that we have available. But while we've traditionally leveraged 8 serial ATA solid state drives and have been limited to 4 gigabytes per second as a result, the latest technology and roadmap will bring us to U.2 NVMe drives, and that will bring our sustained recording rate up to 12.5 gigabytes per second. Again, a very impressive record write speed for a package of this size. This chart illustrates all 3 form factors and where their data rates have evolved over time. The navy blue line you can see starts in 2010 with a 1600 megabyte per second record rate, and you can see in the course of the last 12 years has evolved to 25 gigabytes per second. That's more than 10 times the speed in that period of time. The light blue line shows the portable unit from 2014 evolving to 2022 from 2 gigabytes per second to 12.5. And perhaps the most impressive is the half ATR in the light green line that was at 400 megabytes per second in 2016. And we have expectations to reach 12.5 in the next couple of years. So again, this is just an outline or a graph that shows you how we are constantly increasing our data rates at a high speed. Talk a little bit about PCI Express, because this is critical towards our growth path in terms of storage rates. Leveraging the commercial off-the-shelf technology has been the critical piece of the puzzle here. The chart on the left shows the motherboard introduction date. That date in correspondence to the PCIe revision, which is in the second column, those dates are release dates of motherboards. The technology was announced far before then, but the actual proliferation of the motherboards, those dates are reflected there on the left. The transfer rate per line, the gigatransfers per second, there's a theoretical rate and then a realizable rate. They were affected by both the encoding scheme and also things like the payload size in PCIe and other PCIe overhead, but the realizable rates typically run at 80%. So you can see in 2008, an 8-lane PCIe device was running at about 3.6 gigabytes per second, whereas as we move to Gen 5 in 2022, we're expecting an 8-lane card to run as high as 25.6 gigabytes per second. Moving into 2024 and beyond, as we move to Gen 6, we'll double that again. Again, I show the 8-lane cards because those are common in the data acquisition boards that we make, as well as some of the RAID controllers that we use. But 16-lane throughput is also important to talk about, because there are 16-lane-wide PCIe devices that we use in our systems. And as you can see, the numbers have grown dramatically from the motherboards in 2008 to the motherboards today. Drives are also, obviously, in a recording system, a huge part of the equation. I started with serial ATA because this foundationally was how our recorders started. We've actually started with serial ATA rotating media and then eventually moved to solid state drives. But I talk specifically of solid state drives here because it gives us an apples to apples comparison to the drives that were available back then to the drives available today. In 2003, serial ATA Gen 1 was moving data at a realizable write speed of 125 megabytes per second. That's on a per drive basis. And into 2010, the serial ATA Gen 3 was moving data at 500 megabytes per second. We've been using these drives for a long time. We're able to RAID drives together to create higher aggregate storage rates, which we'll talk about as we talk about RAID cards. But this is just a little bit of a history of where serial ATA has been and what we've used in the past. So RAIDs are it's an acronym for a redundant array of independent disks, and they have two primary purposes. One purpose is to increase the speed at which you can write to the drives. So it does that by a means called striping, where it writes a stripe of the data that's coming from your data acquisition or whatever your source is to disk by striping that data across multiple drives and writing to all those drives in parallel. So you're able to aggregate rates across a number of drives. And that obviously comes with it the addition of storage capacity. But the other thing that RAID offers is the concept of redundancy. And different RAID levels offer different levels of speed enhancements as well as redundancy. I mentioned here that RAID controllers can typically hold up to 16 drives. These are standard PCIe hardware RAID controllers that we're talking about. I laid out a table here that shows different RAID levels because RAID changes its functionality based on the level of RAID that's configured. But there's two particular levels that we use that I want to talk about. The first is RAID level 0. This is the most commonly requested RAID level for our recorder customers. And the reason why is it has the highest performance when it comes to write speeds to disk. It very simply does what I just mentioned, which is stripes the data over a number of drives so it can write to them in parallel, and the rate of a single drive can then be multiplied by the number of drives in the system to provide a much higher disk rate or record rate. The downside to this RAID level is there's no redundancy. So if you have 16 drives that you're striping across and a single drive fails, you lose all of your data. So striping, while it's very commonly used, it does have that downside of not having redundancy. Another RAID level that we don't ever ship with our recorders, but you may be familiar with, is RAID level 1. This is called mirroring. This is very common in a PC where you want to have redundancy on your operating system drive. You simply add a second drive to your system, set it up as a RAID level 1. All the data is mirrored between the two drives. So if you lose a drive, all your data can be recovered by simply switching over to the second drive. So RAID level 1 is great for those types of low speed or a requirement that doesn't include the need for a higher speed to disk than what the disk itself can handle. But RAID level 1 does add that mirroring capability. The other RAID level that we do use, and is a really nice combination of performance due to striping plus redundancy, is RAID level 5. And what RAID level 5 does is it takes a number of drives and it stripes data across all of those drives except for one that it uses as a parity drive. So it calculates the parity on a bit-by-bit level for every bit that's written across those drives. And what that allows is that if any single drive fails in the system, you can recover the data very quickly and easily. It comes with very little overhead. It has a slightly lower write performance than RAID level because there's one less drive that you're writing to, and in addition to that, there is obviously a little bit of processing that needs to be done to calculate the parity bits, but it offers a really nice combination of speed and redundancy, and this is something that our customers commonly order as well. So RAID level 0 and 5 are the two RAID levels that I would say 95+% of our customers order from us with our Talon recording systems. RAID level 6 is the other one we see sometimes because it allows for multiple drive failures, but it does come with a penalty of speed. So in cases where the speed is not as important, RAID level 6 sometimes is available. And as you can see, there are other RAID levels here that I won't go into at this moment. So we talked about SATA drives, we talked about RAIDs and striping them, but let's talk about where technology is today, and that is in NVMe. NVMe is non-volatile memory express, and this is the next generation storage specification that really is replacing serial ATA. It uses PCI Express as its interface into the drive and to communicate with the controller. And what that does is it provides extra or additional serial lanes into the drives. So serial ATA has had a single half duplex line, serial line for communicating, for moving data to and from the drive. NVMe is actually leveraging the PCI Express 4-lane channel bonded interface, so you have much wider bandwidth and throughput to the drive. In addition to that, it leverages the newer generations of PCIe. So as PCIe evolves from one gen to the next, the drives get faster and faster, or the interfaces into the drives get faster and faster. They have write speeds already exceeding 10 times what serial ATA 3.0, which is the last version of SATA that was released, 10 times those speeds already. Again, they leverage that PCIe roadmap, so that provides that path to doubling the write speed every few years. So this is an excellent direction for storage technology to go in. NVMe is available in several form factors, and we'll go into that in detail. And just like serial ATA drives can be striped together in a RAID configuration, NVMe drives can be striped together in a RAID configuration. When it comes to NVMe drive packaging, there's a few different form factors that we need to talk about. The most popular flavor, and the one that you're probably most familiar with, is the M.2 form factor. This drive, or this form factor, was initially designed for laptop computers to replace the 2.5-inch SATA drive that resided there. It provided both a smaller footprint and a speed enhancement over what was currently in a serial ATA 2.5-inch drive. It typically has a 4-lane PCIe interface, although some drives and motherboards support only 2 lanes, still much faster than what you would see with serial ATA. Its nice small size makes it a very practical form factor for small packages, but it's limited in its capacity due to the thermal management that you would need to have when you're trying to pack dense amounts of data onto such a small package. So that leads us to another package that is the more popular one now in data center market, and will be more popular, or has become more popular, in the recording market, which is the U.2 package. What makes it a really fantastic package, it's the same form, fit, and function as a standard 2.5-inch SSD. So a lot of chassis that have the front panel removable solid state drives can be re-architected to leverage these drives, and for our customers, it's the same package that they're used to. It can handle a considerable higher capacity than a standard M.2 drive, but it is a Gen 4 or Gen 3 or Gen 4 PCIe interface with 4 lanes wide. So it's a fast drive with a good amount of storage in a familiar package. Another package that you'll commonly see is a native PCIe card that can handle up to 4 banks of memory. What's nice about these cards is they typically have 16 PCIe lanes at the PCIe edge fingers, which means you could install it in a 16-lane slot and really have a high bandwidth, high throughput card that could really move data quickly to and from disk. And as I mentioned, there could be 4 banks of memory that are switchable via PCIe switch or a RAID that's built into the native card itself. Those slots could be 4 independent M.2 slots, or there could be native solid state storage installed on those cards. The downside to those cards are that they are PCIe and they're not easy to move in and out of a system. So if you're in the recorder market where your customers are looking for drives that can be easily removed, that can be moved in and out of classified areas, or a system that can be sanitized quickly, having to deal with a PCIe card that's embedded in a chassis is not the greatest option. Also in the data center market, from a standpoint of a drive failure, having to open up a chassis and remove a PCIe card is not practical. So these are less popular than I think they were intended to be. The most interesting drive package is the newest one, and this is the ED-SFF form factor. That's Enterprise and Data Center Small Form Factor. Intel started this a few years ago with what they call the ruler. This is also known as the E1.L form factor. The nice thing about this is they support PCIe gens all the way up to Gen 5, and the E1.L is a long stick that could hold quite a bit of storage on it and also allows for proper thermal management due to the spread out form factor. The E1.S and E3 form factors are also going to become very popular form factors, and I'd like to talk about that a little bit here. So E1.S is a little bit bigger than an M.2 drive. What makes it more practical is that it can hit the higher PCIe gen rates, and it has heat sinking variation in terms of the thickness of the drive. So it's intended to hold a higher capacity than an M.2 drive by nature of the varying thickness that can be supported by it. But the E1.S, while it hasn't gained much popularity yet, it will gain more as PCIe Gen 5 begins to proliferate through the motherboard market. The E1.L drive, which is that ruler form factor that I mentioned, again, a really nice form factor. It's longer at 318.5 millimeters, but again, it spreads the heat out a little bit better, has the ability to include a considerable amount more storage than the E1.S, and it has varying heat sink thickness to it, so it can handle the heat dissipation that you'll see at these higher speed memories, especially when operating at PCIe Gen 5. The form factor that I'm actually most interested in is the E3, and of course the reason why is because it follows the 2.5-inch SSD footprint, just like the U.2 did following the SATA 2.5-inch footprint. This will follow that same footprint, and it will come in a package that looks and feels exactly like a standard 2.5-inch drive. The thickness will vary, similar to how it did with SATA and with U.2 in the beginning, from a 7.5 millimeter minimum thickness to a much thicker drive based on the amount of storage and heat dissipation. And I think what you'll see with that drive is, as technology advances, the thickness will eventually reduce down to that 7.5 millimeter. But again, this is going to provide large storage capacity, a familiar footprint, and the PCIe Gen 5 support most importantly. So these will be the fastest of all the drives with a very large amount of storage capacity available in them. So let's talk about these drives today and the roadmap. The Gen 3 drives, currently in a U.2 form factor. I've added the theoretical read and write rates here in this chart, as well as the realizable. These realizable rates are rates that we've actually measured. So a 2.2 gigabyte per second write rate at Gen 3 is excellent. As a data point, serial ATA Gen 3 would cap out at about 500 megabytes per second realizable write rate, so you're going over 4 times faster with just the Gen 3 version of U.2. Gen 4, we're up to 3.5 gigabytes per second in the realizable write rate. What will happen is flash technology, the flash memory will eventually get faster and faster, and the realizable rates will start to approach the theoretical rates. But right now, these rates are what we are measuring. And when we move to Gen 5 and that EDSFF form factor, we have no measurements yet for this, but the expectations are to hit realizable write rates of 7 gigabytes per second. So again, this is on a single drive basis. These are phenomenal rates, and remember that we can always stripe multiple drives together to aggregate higher rates, and that's how we start to get to these 25 gigabyte per second and beyond recorders. An excellent roadmap leveraging PCIe's generations and the newer technology in storage. This was a nice chart that sort of showed the history of the M.2, U.2, and some of the newer form factors, both the past and projecting into the future. What you'll see is in the orange, the M.2 form factor, while it grew in popularity, it's expected to shrink as the new Gen 5 E1.S and E3 form factors start to proliferate, as well as the ruler, the E1.L. And you can see U.2 has a firm foothold in the market because PCIe Gen 3 is still very popular in data centers center servers and will continue to be so for quite some time. So, as I mentioned, these NVMe drives can be rated together for striping to improve performance as well as to add redundancy. But I wanted to talk about just two different types of RAIDs. We've been talking about hardware RAIDs in this presentation so far, and that is the desired RAID configuration because it offers the best performance. The dedicated RAID has a controller chip that essentially offloads the CPU from having to do any of the striping. It's all done at the hardware level, and it's going to offer the best support. Current RAID, NVMe RAIDs are hitting rates as high as 25 gigabytes per second. The other option is what Intel calls VROC, which is it's a virtual RAID on chip. It allows the Intel processor on the motherboard to perform the striping, and while this is not considered a pure software striping mechanism, it really, because it is using a CPU, it really is software striping. So there is some impact on its speeds. It's not able to hit the rates of a dedicated hardware RAID, and it only works with the Intel Optane drives currently. So the nice thing about it is it eliminates the need for the additional hardware. So in the case where it is able to perform at the speeds needed and you can get the reliable performance, VROC is an option to a hardware RAID card. Talking about some of the products that are going to utilize this technology, I mentioned the Quartz RF SoC. It has two 100 gigabit Ethernet ports. The Model 2757 recorder has QSFP28 ports with MPO transceivers to receive data or receive the optical interfaces connections from the Quartz RF SoC. This recorder will be using a Gen 4 or Gen 5 motherboard in the future to hit the 25 gigabyte per second rates. And this is nice because it allows us to take all 8 channels from the RF SoC via the 200 gigabit Ethernet interfaces and record them at the full rate that those 100 gig E lines support. So again, using all of the technology that we've spoken about in this presentation, we'll be able to handle the maximum amount of data that can be offloaded by the Quartz RF SoC. We also have some future products that will leverage this. There are new high-speed A to D converters that are coming out that will allow what we call direct RF digitization, meaning the ability to sample the RF spectrum all the way up to K-band. These are technologies that you'll be seeing in future products. These products will produce tens of gigabytes per second. So it's extremely important for us to have a recorder that can handle these types of data rates. So what you'll see on these cards that are performing this directed digitization, both PCIe interfaces that will be using Gen 4, Gen 5, and Gen 6, as well as high-speed optical interfaces from 100 gigabit Ethernet and eventually expectations to go to 200 gigabit Ethernet. So as more and more data is produced by high-speed A to D converters and interfaces are expanded on our data acquisition cards to move data, it's going to become necessary for our recorders to be able to handle that. So again, the PC motherboard that we're using with the NVMe storage technology is the interface that will scale with this technology as we move forward. So to wrap things up, Talon recorders, the point of this presentation is that we are using commercial off-the-shelf hardware, and this is what allows us to move data faster and faster. As you see, we've been doubling data rates every few years, and we will continue to do so as a result of using this type of hardware. PCIe, doubling those data rates is a key part of this. The storage media, as we talked about, it's evolved from serial ATA to NVMe-based storage, and even NVMe is migrating in terms of the form factors of their drives to support higher and higher PCIe speeds. The data center market is a big force in driving this, as obviously this is what the drive manufacturers are catering to, trying to make faster and faster drives for that market. These new form factors, again, we talked about the E1.S, E1.L, and the E3 drives. They're intended to handle higher PCIe interface speeds and to have better thermal management with these new packages. And our Talon recorders offer these in all the different form factors that we showed, including that half ATR form factor, which is a mil-specified chassis. Again, as these drives get smaller and they get faster, we're able to hit these higher rates in smaller and smaller packages. I appreciate your time. Thanks for listening, and I welcome any questions that you might have. Thank you.
Okay, a few of you have already submitted questions, so we'll jump into those in a moment. If you'd like to submit a question at this time, please type it into the Ask a Question box and hit the send button. Also, please take a moment to complete the feedback form that'll appear on your screen at the end of the webinar. Okay, Chris, our first question for our audience today is, you mentioned direct RF sampling. Can you tell us a little bit more about the roadmap for future products?
Sure. Well, we're under NDA with a number of chip manufacturers right now, so I can't dive too deeply into this, but I can say that we're working towards direct sampling of signals all the way up to K-band. So this will create a tremendous amount of data, which is why it's so important that we evolve our recording capabilities towards faster storage media.
Okay. The next question I have is, do you expect Ethernet to be the primary interface for moving data off of your data acquisition cards moving forward?
While Ethernet's temporarily eclipsed what was possible in terms of data rates with PCIe, the next generation of PCIe has caught back up. So I think there will be a place for both interfaces when it comes to the high-speed, data movement. You may see cards that include both interfaces or versions that contain one or the other. Either way, I do see a path for both Ethernet and PCIe interfaces.
Okay, very good. And another question is, do you expect PCI Express to continue to double data rates, and for how long?
So there was a long delay moving from PCI Express Gen 3 to Gen 4 as chip manufacturers struggled to hit the serial interface speeds. There was a breakthrough over the last couple of years, and we've quickly jumped from Gen 3 to Gen 4 to Gen 5. Gen 6 is on the roadmap, and it's expected to proliferate in the next couple of years. So I expect this trend to continue for at least another 5 years. It's kind of hard to see beyond that, but I believe there is a roadmap at least for 5 years with PCI Express.
Okay. Well, I'm afraid we're out of time for today. For those questions we didn't have time to get to, we'll get back to you via email. And that concludes today's presentation. On behalf of Electronic Design and Microwaves and RF, I'd like to thank Mercury for sponsoring today's event, and of course, all of you for joining. Have a great rest of the day.